Thank you, everybody. Thank you so much to SWCD for hosting this awesome event. Thank you for the Southern Ute for hosting us. I wasn't able to enjoy the casino last night, but I do have a 5-week-old, and I'll tell you, I hit the jackpot of sleep last night. It was awesome. So I'm in the business of creating climate-resilient forest and water supplies. Is that better? Sorry. I'm in the business of creating climate-resilient forest and water supplies. I'm based out of Silverton, Colorado, and I work for the Mountain Studies Institute, 2 years. I'm going to present quite a bit of research that I've done on myself in my PhD, as well as my current work, as well as research that I've collaborated on, as well as research that I find valuable to this discussion. And really, I'm going to discuss the interaction between forest structure and water resources. Keep telling me if you can't hear me. So there are two major interconnected issues that the Western United States faces. The first is an issue of our snowpack, and we've talked about this quite extensively throughout the last discussions, but I want to speak directly to it. So you're looking at a paper from Lee et al. 2017, and they look to quantify not only where does our water come from, but what type of precipitation is it? Is it snow or is it rain? So when you look at this figure, the blue is snow-dominated, and the yellow is rain-dominated. And we can see that there are a number of areas, the Rockies, the Wasatch, the Northern Rockies, the Sierras, and the Cascades, that dominate our snow production. So we can say pretty unequivocally, about 25% of the area generates roughly 90% of the water that we have available. And of that water, 50 to sometimes 99% of that water comes from snow. So snow is our primary issue for thinking about our water supply in the Western United States. Now, if we look at snow and snowpack cumulatively over time, we can see there's an unfortunate trend. So this is MOTE 2018, and they took snowtail data from out the Western United States and culminated into total volume. And what we can see from this figure is we've seen about a 21% decline that equates to 29 million acre-feet loss in storage. Now, there's a lot of intelligent people in this room. The largest reservoir in the United States, the maximum capacity, is 29 million acre-feet. So we've lost that storage already. This issue is local as well. So you're looking at 3 different figures here from the Florida River. This was a project I did for Durango Water to assess their water availability and possible storage implications. The top graph is looking at annual precipitation. The middle is your water yield in terms of a runoff depth. If you're interested in what that parameter is, I'm happy to explain. And then the bottom is something that we call a runoff ratio. And you can think about that as the efficiency of the watershed to generate water per given input of precipitation. So starting at the top, if we look at this trend, it is significantly declining throughout time. Statistically, I'm using that word specifically. And we've seen a decline if we look at an average of 86 through the 90s, through the first decade of the 2000s, a decline of about 12%. If we compare that same range, the late 80s to 90s to our last decade, it's a 20% decline. If we look to total runoff, those values are actually more stark. 27% decline, 35.7% decline. This is again for the Florida River. The most startling thing to me in this analysis, and this is very simple data, I just took this from gauges, this is all observational data, this is nothing modeled, anybody can download this data. The most stark thing to me was that our runoff ratios were declining. So not only are we getting less water in and less water out, we're getting less water out for the same volume of water in as we were before. That's a challenge. This leads to our second issue, increases in wildfire throughout time. This is a paper from Idaho State University, 2017, and we can see that fire frequency is dramatically increasing as we move throughout time. Well, what about intensity? So on the bottom, we have median size of our wildfires, and the median is staying very flat. So what that says to me as a scientist is that wildfires on average, if we look at the median, are staying at the same size. But if I look at the mean, which accommodates more outliers, maybe our catastrophic wildfires, those are increasing. So our large wildfires are getting larger. So we have less water, and we get large wildfires getting larger, and we're seeing the frequency increase. This has dramatic impacts on human communities. This is Paradise in California, completely annihilated, wiped off the map. I have friends that lost homes in this fire. But it also has profound impacts to the hydrology, and this is really what I study. So this is a burn system, and if we have a simple mass balance or a water budget here where Q equals discharge, P equals precipitation, E is evapotranspiration, ET, INT is interception, and S is storage. So when I burn a system, I change the way this water budget functions. So I decrease evapotranspiration. The plants don't have stomata to transpire. I increase interception, which is the process of snow falling on top of trees and then maybe sublimating or evaporating out because there is no canopy. And I probably decrease my storage or my delta in storage because of either hydrophobicity or soil sealing. So that water has to go somewhere because this is a mass balance. So we've seen in a lot of cases that we see an increase in discharge. So scientists, and this is an old question that people have been answering for a long time, said, hey, if we see this increase post-wildfire of surface water yields, can we emulate that with wildfire mitigation? Can we address two issues? Can we reduce wildfire and increase flow? So my research aims to answer that question. In my PhD, I studied a basin in Ashland, Oregon, which is just north of the California border, and what you're looking at is a number of different treatments throughout time. These were surface and ladder fuel treatments, underburn, mastication. In these basins, there was a west and an east. The west had about 15% treated. The east had about 36% treated. And we expect to see increases at about 20% treatment. But that's kind of a bad metric, because if I just say, hey, I've treated 20%, well, how did you treat it? So if we look at some more realistic numbers like canopy cover, we could see that these treatments actually didn't have that much of an impact. They're roughly about 4 to 6% declines in canopy cover throughout the treatment period. So what happened to the hydrology? I only had gauges at the base of these basins, so I could only understand it at the basin scale. So these, again, are runoff ratios, so the relationship between precipitation and discharge. The left is the west, the right is the east. Those red bars are the percent treatments per year, and then those blue bars are our trend over time. Both of these look identical, and one basin was treated about double of the other. So I would have expected to see some differences. That was the first thing telling me I didn't get the result I wanted. The second one is I ran the statistics and it was non-significant and it was a downward trend over time. I would have expected us to see increases in water yield as we increase our treatment. So unfortunately, in this case, low impact treatments do not have a significant impact on water yields. Oops, wrong direction. Another paper that actually just got accepted yesterday and will be in publication in Ecohydrology that I'm a co-author on looked at the Sage-Hen Basin in California. But in this case, we were actually able to sub-nest our watersheds and get discharge data for individual treatments. And I want to point you to Basin 2, because that was the basin that we treated the most. So if we're going to see a response, we're going to see it in sub-Basin 2. And what was very cool is from some remote sensing products, CBOP, which looks at evapotranspiration, and LiDAR data to get canopy cover, we were actually able to show and demonstrate quantitatively, yes, if you reduce canopy cover, you will reduce evapotranspiration. So we were like, okay, we're on to something here. And then we went to the numbers, and we created full water balances. And again, I'll point you to SGH2. And here what you're looking at is water balances over time. So that black is precipitation, the blue is surface water discharge. I've got evapotranspiration in green, and then storage in red. And those red bars, those red vertical bars are where we did treatments. But again, look at SGHO2. We see that red bar, and we see an increase in discharge. But you also see an almost identical increase in precipitation. So we can't unequivocally say, oh, this increase was because of the treatments. And when we ran the statistics, we were actually able to explain variance in discharge by over 80% just by precipitation alone. So this basin was completely precipitation dominated. It didn't matter that we treated over 60% of that subbasin. We still saw no response. It was precipitation dominated. It's not working. So that leads me to further solutions. What can we do? We've gone back to the drawing board. People have approached us with projects that hasn't panned out, so let's figure it out. So we're implementing something new called snowtography that was developed by the Nature Conservancy and United States Department of Agriculture and Western Water Assessment. And what we're doing here is low-tech systems to go across varying degrees of forest structure where we can get snow depth, we can get snow water equivalent, and soil moisture. And we're building a network, and we're so grateful for SWCD for funding a new episode of this. We'll be putting in 2 new sites here in Colorado. We've got 3 currently, with the long-term goal of creating a regional network to inform foresters, hydrologists, and land managers to, is there a way for us to geoengineer forests to be climate resilient, retain and accumulate more snow, and be resistant to wildfires? Thank you so much for your time.